This material has been excerpted from the college television course, The Mechanical Universe, and re-edited specifically for use in the high school curriculum. The Mechanical Universe is funded by the Annenberg CPB project, made possible by a grant from the National Science Foundation.
Mariner 10, 1973, to Venus and Mercury. An exquisite vessel, a scientific explorer launched across the solar sea. Viking, 1975, to Mars. Another mechanical marvel, launched in search of answers. Voyager, 1977. To Jupiter and to Saturn, to Uranus and to Neptune. Mariner, Viking, and Voyager. This century's Francis Drake, Ferdinand Magellan, Eric the Red. Launched to discover how the planets were created. Without even the aid of a lighthouse, how can a modern mariner or any other space-age vessel sail from here to there? And once launched into the cosmic seas, who navigates? Caltech's Jet Propulsion Laboratory, JPL, Pasadena, California. Nerve center for exploration into the endless frontier of space. The cerebral cortex of NASA's unmanned planetary program, the Deep Space Network Operations Center. There are countless problem solvers in the space age, but only a few are qualified to solve problems in outer space itself. One age-old problem of outer space has to do with getting there.
I suppose it would be possible to fly a spacecraft on a straight line from one point to another in the solar system. It would require an exorbitant amount of propulsive capability. It surely is not the best way to do it. In fact, in flying from one place to another in the solar system, we use one of Kepler's laws, which tells us that the planets move around the sun on ellipses, and the spacecraft will follow exactly these same laws.
Ignition. Obviously, to aim toward the planets with brute force alone is to miss the point entirely. Clearly, present-day space navigators look to the future by way of the past. Kepler's 3 laws stated how the planets orbit the sun. Newton explained why Kepler's laws work. Now, no matter how futuristic the problems, space navigators use Newton's and Kepler's laws as operating principles.
The way we get a spacecraft from Earth to Mars is to put the spacecraft in an independent orbit around the sun that necessarily intersects the orbit of Earth and the orbit of Mars. In fact, the launch vehicle has to impart enough speed to that spacecraft right after launch so that it will coast all the way from Earth to Mars once the launch vehicle burns out 30 minutes after liftoff. To
travel between 2 points in space, A craft coasts to its destination in orbit around the sun, just as if it were an orbiting planet. The path of a spacecraft from one planet to another is called a transfer orbit.
For the Viking mission, we were quite limited in selecting the transfer orbit because Viking was the most massive interplanetary spacecraft ever launched. The then most powerful launch vehicle, the Titan Centaur, could just barely get us to Mars. The classical transfer between two planets is referred to as the Hohmann Transfer. We followed a transfer very close to this. It's one in which we launch from Earth tangentially at the lowest point in the orbit, that is the point closest to the sun, and arrive at Mars at the highest point, the apoapsis point, the most distant point from the sun. So we have an orbit that just manages to connect from the Earth's orbit to Mars' orbit. In fact, the spacecraft does 1/2 a revolution in this orbit to make the transfer.
Getting there may be half the fun, but the trip can't just start any old time. No matter how elaborate the preparations, the whole crew has to wait until it's time for launch.
The problem of getting a spacecraft from one point to another in the solar system is rather like shooting at a moving target with a rifle. There are two parts to the problem. You have to be sure that the target is within range, and you have to establish the amount by which you're going to lead the target so that it doesn't pass you before you get there.
Just as Kepler's third law fixes the length of an Earth year, and the length of a Mars year. It also dictates how long a spacecraft, coasting in an orbit of its own, will take to get from the Earth to the position of the orbit of Mars. It takes about 8.5 months. In order for Mars to be waiting when the craft arrives, it has to be launched when Mars is just 44 degrees ahead of the Earth. That alignment is called an opportunity. Space navigators must wait for just the right moment, when a coasting orbit will take the spacecraft from the position of the Earth to the orbit of the target planet, just when the target planet arrives there. That moment is called an opportunity. And opportunity doesn't knock at the same time for all planets. Prospects look good for Mars about every 2 years. An opportunity to visit Venus presents itself every 19 months. And for Jupiter, each 13 months. When these times come, space navigators must be ready to move quickly through a launch window, a few fleeting moments each day when the rockets must actually be fired.
For each day, there is a fairly restricted time within which we could launch. This problem is quite similar to one where you might be riding on a carousel and playing catch with a friend standing off to the side. For each revolution of the carousel, you'd have a fairly short range of time where you could see your friend and could throw the ball to him. On our revolving carousel called Earth, the problem is very similar. Each time that the Earth comes around, we have an alignment between the launch site and the direction in which we need to depart from Earth. So the problem is one of waiting until we get this alignment, and then we launch.
The carousel called Earth is itself in a nearly circular orbit around the Sun. Any increase or boost in speed creates a bigger, more eccentric orbit. To go from an Earth orbit into a Mars transfer orbit requires a boost of exactly 2.9 kilometers per second. But the first task is to escape from the parking orbit around the Earth. A rocket thrust will boost the craft into a hyperbola that drifts to infinity at just the right speed of 2.9 kilometers per second. And the thrust must come at just the right moment. That moment is 7:56 p.m. local time. The Sun does the rest of the job, bending the trajectory into a Mars transfer orbit. If the destination is Venus rather than Mars, the basic idea is the same. But now, the journey is inward, toward the Sun. Blasting off in the morning at 7:40 a.m., the craft escapes from the Earth. But this time, it's going backward, relative to the Earth's orbit, losing speed and falling inward toward Venus. To make the trip meant first of all overcoming gravity, just to escape from the planet Earth. But even then, and even given the grand once-in-a-175-year opportunity, it still couldn't have been done without the help of gravity itself.
The principle of gravity assist is really pretty simple. What we do is we use the gravity of a planet to change the speed and direction of flight of a spacecraft as it goes past the planet. Now, of course, when I say change the speed and direction, I mean really with reference to the Sun. From the point of view of the planet, nothing much happens. The spacecraft is out here approaching with a certain speed. It speeds up, whips around, and leaves. Same speed leaving as it had coming in. But from the point of view of the Sun, it's quite different. The planet is moving past the Sun. And in that motion is imparted to the spacecraft by the gravity of the planet. So the spacecraft comes in, goes out, and now from the Sun's point of view, it's moving much faster. The spacecraft has, well, it's really stolen. Stolen a little bit of energy and a little bit of momentum from the planet. And the planet has given that to the spacecraft, so it's on a completely different orbit around the Sun.
Both Voyager missions got their first gravity assist from the planet Jupiter, propelling them onward toward Saturn. But to appreciate the concept, it's not necessary to go quite that far.
You might think of it this way. Suppose you imagine a baseball game. Here's a batter, and he's going to bunt. So he holds the bat absolutely still. The pitch comes in, bounces off the bat, and down onto the turf and rolls away. The only thing that the baseball bat has done in this interaction is change the direction of flight of the baseball. It hasn't added any energy to it. But if the batter's swinging, the bat is moving. The bat has energy. When the bat hits the ball now, it adds quite a bit of energy to it, and in fact enough to get over the fence and be a home run. It's the combination of the energy which the pitcher gave to the ball and the extra energy the ball got from the swinging bat that is now enough to carry it over the center field wall. Of course, like most analogies, this one isn't perfect. A spacecraft doesn't bounce off a planet like the ball off of the bat. The spacecraft approaches the planet, and it's the gravitational pull of the planet that causes this interaction. It's not a physical contact.
If Jupiter really did hit Voyager, that would be the ballgame. While there's no physical contact, however, there is a striking connection between baseball and physics. Jupiter doesn't stand still. It moves. And like a swinging bat, it gives up some of its energy to the ball of Voyager as it flies by. Celestial scientists from Johannes Kepler onward could calculate the motions of the solar system, and any great scientist who understood the orbits of the planets held within his grasp a profound and truly heavenly knowledge. But for 300 years, even to the greatest minds, the heavens remained within reach of the intellect alone. 3 centuries would pass before the first hesitant steps beyond the barrier of Earth's gravity were taken, to finally allow scientists to take part in, rather than observe from afar, the worlds beyond the planet Earth. Navigating as well as calculating, making heaven passable as well as possible. That is the miracle of the space age. That's what the father of classical mechanics might have dreamed of. But that is what the space navigators made reality.
This material is based upon work supported by the National Science Foundation under grant number SPE 8318420. Any opinions, findings, and conclusions or recommendations expressed in this program are those of the authors and do not necessarily reflect the views of the National Science Foundation.